But without further ado, this is a delicious meal I had last night. I appreciate the hospitality and the opportunity that OpenSSF has expanded to be able to come and present such work and with such beautiful tasting food and looking as well. So I'm looking forward to spending the next 2 days also being able to taste food, visit Lotte World, etc. But without further ado, getting to the content, I want to highlight some research that we've been doing at UC Irvine. I'm a fourth-year PhD student, or one might call a PhD candidate, and have been looking into some of the AI and ML vulnerabilities in open source projects. So you could kind of expect a more academic perspective of the problem, but of course there are practical implications that we plan to discuss and actually dive deeper into when we plan on writing and publishing this paper. So to provide you some context of the problem, so for the scope, let's assume that there is a bug in some type of GitHub project. And usually when that's the case, and we have things like bug bounty programs involved, we'll have what we call a bug hunter. Bug hunter submits and creates a bug report to, let's say, a group of open source maintainers, which we have here on the bottom left. And they find this bug where they write like a POC, things that you might expect in a bug bounty report, which usually contains very enriching information if written as expected. For the scope of this problem, which I highly encourage you to look at the slides in the presentation, there are clickable links that take you to this bug bounty program called Hunter, which essentially now is a AI ML open source bug bounty program that is owned and governed by Protect AI. As we all know, or most of us know in the room, when we do have a valid vulnerability, in an ideal world, for instance, in the United States, this would become something like a CVE, for example, which eventually and should get routed to the National Vulnerability Database, which again is based in the United States. But for the scope of this project, we're going to focus on how these tools could, for example, provide disclosures to affected projects and tooling capture. So we'll assume that this is in the space of, like we see on the top right, the Vulnerability Disclosures Working Group space. However, for the focus of this project is actually these bug bounty reports. What kind of bugs do they contain? Do they contain what we expect? What are aspects that we do and maybe not care about so much? So moving forward for the rest of this presentation, we're going to be focusing on vulnerabilities that come as a source of some type of bug bounty report. Our research questions that we have in mind for this project is, what are the most frequently reported AI ML open source vulnerabilities? How do these vulnerabilities compare to what is expected in AI ML software? So for example, we have our OAuth's top 10 list in ML. We have the OAuth's top 10 list for LLMs. And I think there's actually some kind of security report that just focuses on agentic AI as well. So how do these vulnerabilities compare to those? And how do key stakeholders, for instance, our maintainers who are actually reviewing these reports, handle and triage AI, ML, open source vulnerabilities? Our contributions that we're planning to do and hope to release as soon as the paper is published or we have a preprint is we are curating the largest data set of disclosed AI, ML, open source bug bounty reports. We are using a mixed method study and approach to identify and categorize recurring vulnerability types unique to AI, ML, open source systems. And lastly, we are analyzing how these security reports differ from traditional vulnerabilities by things like bug type, severity distribution, and fixed latency. So for example, how many are fixed versus how many are not fixed. To give you kind of like a more bigger picture idea, what I'm planning to do for these slides is just to give you a couple of takeaways per group of data that we have, which you can again find in the slides, which is online. So for here on the left, we have a table of, for example, the NVD 2022 vulnerability distribution grouped by severity, which is the most recent, compared to what we have in our data set versus what some other, one of our related works has also reported about AI and ML open source vulnerabilities, followed by the top 5 CWEs, so common weakness enumerations, that come up in our data set. So for example, the most popular one here is path traversal, followed by improper access control, etc., which should look somewhat familiar for those of us that are familiar with top 10 OAuth security lists. The first thing I would like you to take away from this slide is bolded. Vulnerabilities in our data set are disproportionately affected by high and critical severity vulnerabilities. When compared to the NVD, this comprises of 77%-ish vulnerabilities are either high or critical in our data set versus the 24.6% that is in the NVD, highlighting pressuring risk in the AI software supply chain. Again, this is more of a big picture. You can see in a somewhat related work, we saw similar results, but in our data set, we have a more complete picture. AI open source software is disproportionately affected by high and critical vulnerabilities. Also, they reveal that a range of top AI ML OSS vulnerabilities fall outside expert curated lists like OWASP. This mismatch might suggest some misunderstandings or really just context undermining common issues in emerging OSS AI ML vulnerabilities. For example, it seems that there's more traditional vulnerabilities that may or may not be coming up in these projects. So we're curious about investigating deeper kind of what's going on here. To summarize, the most frequently reported AI/ML vulnerabilities are traditional software flaws, such things like a denial of service, cross-site scripting, and some other familiar-looking vulnerabilities from the top 10 original OWASP list. And also that the absence of adversarial ML and agentic AI risks, a mouthful all day, in the most common CWE categories suggests that AI and ML OSS vulnerability classifications are still anchored in traditional web and infrastructure security paradigms and challenges. So what we plan to do is kind of expand upon this and create a taxonomy to map out the types of OSS vulnerabilities that we're finding in these AI and ML projects. On the other end, a different perspective is how are the stakeholders dealing with these vulnerabilities? So for example here, we have a table that shows how fast these vulnerabilities are resolved after being received as a bug bounty report, for instance, showing that most of them are resolved within 3 months, as you can see by this 81.5%, and which makes up approximately 84% of vulnerabilities that we're seeing are resolved within 3 months, which is a good thing. However, on the other side, we also see a lot of these are not fixed. I think the number is 49.5% of the vulnerabilities in our data set that are already disclosed have yet to be fixed as of November 1st, 2025. What I'd like you to take away from this slide is that maintainers are doing a really good job of reviewing and patching these vulnerabilities. The fact that they're taking around 86 days to review, which is comparable to open source or professional organizations that have a policy of disclosing vulnerabilities within 90 days. However, yet only half of them are fixed, and also 44% of these approximately CVE assigned vulnerabilities are actually missing from the NVD, that is the National Vulnerability Database, which I encourage you to look at the links that I've included in the slides to learn more about that. Lastly, there is a disproportionate unfixed vulnerability distribution that is 48.6% high and 23.6% of critical severity vulnerabilities remain unfixed, particularly those revolving around access control and path traversal. Further, we did some statistical tests and found that maintainers like money, and of course, if you're a bug hunter, you also like money, meaning what I'm trying to say is that these fixed vulnerabilities receive significantly higher bounties than the unfixed ones, suggesting some kind of incentive to fix the high-repairing ones first. Despite comparable review times to professional organizations, these AI and ML open source vulnerabilities exhibit critical gaps in remediation and visibility. That is, only about half are fixed, and nearly half of the CVE assigned ones never reach the National Vulnerability Database, undermining automated detection and patching pipelines, which of course are initiatives that OpenSSF Vulnerability Disclosures Group is one of their currently in progress projects that hopefully we can deploy to more open source projects. Lastly, high severity vulnerabilities dominate unfixed cases across some of these more common OWASP or what we would call traditional web application vulnerabilities, especially in access control and path traversal. And bounty incentives, more money equals more fixes. Bounty incentives, they correlate strongly with fixed likelihood via some statistical tests that we performed in our data set. And what we plan to do is get a deeper understanding of maintainer perspectives, which we do have 2 top-tier security papers at Unix and IEEE Oakland or SMP, if you're more familiar with those acronyms, that are more in the general side. So we plan to delve more into this AI, ML, open source space. With that, thank you. I've included a link to my personal homepage that includes things like publications, contact info. You can reach me at my UCI email, which is jessya1@uci.edu. And thank you again for the space and openness to be able to come over here and present this work.
The other connector is...
Yeah, it's still there.
Yeah, okay. Thanks.
Yeah.
All right. Just a couple more talks until you can